Okay, so lecture 5, we're finally going to get some answers. They're gonna be some of the easiest questions a structural engineer might design, but you're gonna get some real answers. You're gonna get the real equations that we use to design things. But as you've seen me do for you most things I show you, there's usually a table that shows most of those things. So we're gonna go through, we're gonna understand what's happening. We're going to talk about steel a little bit. I'm going to show you all the equations, how they get calculated, and we're going to have to do some. You will have to, and I will go through some with you. So I'll go through 2 examples. You're going to do one in the assignment, and then in the exam, there will be a little bit of that. There has to be. It's part of the accreditation process. We have to go through that. But I will also show you some tables where the calculations have already been completed and tabulated for us. That means that even on the ones you have to do the calculations, you can probably get a pretty good idea of what the answer is, or at least a check for yourself that you've done it right. So today we're going to talk about steel column design. We're going to go back and touch just a little bit and do a quick refresher on axial and I guess bending stress and strain, but axial is what we're kind of focused on today. I'm going to give you a quick intro into steel members. I know we talked about some last term, but we just need a bit more information now. So I'm just going to give kind of a quick overview of that stuff, and then we'll jump into the equations. So it is early on Thursday morning for me. My kids have been back at school all week, but as you can imagine, everybody in the world who I've been putting off for weeks and weeks and weeks now very much needs their stuff. So it's been a madcap week. Hopefully next week I will be able to breathe just a tiny little bit, but I'm very excited to be able to start getting into a slightly better routine again. Okay. So, axial stress and strain recap. Remember, stress is force divided by area. And we keep all of the, when we're talking about stress and when we're talking about modulus of elasticity explicitly, we tend to put things in newtons and millimeters. So usually we'll translate all of these into newtons and millimeters. Strain, which is a measure of stiffness, I guess, somewhat, is the change in length divided by the original length. And modulus of elasticity is our stress divided by strain. Knowing these 3 equations, we can combine them and rearrange them as needed to maybe find the bits of information that we need. Look at this here. Stress equals force divided by area. We could rearrange this to be force equals stress times area. And if the well, we're going to get to this. I'm going to hold my peace on that for a second. We'll jump into that a little bit. Okay, just a quick kind of bit of information about steel sections and their properties, because we now are going to need to know a lot of stuff about very specific steel members. So most of what we're going to look at in the next few slides is information that comes out of this book, but you have tables for, there's 2 tables that are in this week's modulus that we're going to use this week. The first little bit, we're going to look at the steel sections. And so that's up there for you. Now, within this, we have 2 different types of members. We have hot-rolled members and cold-rolled members. Hot-rolled members are large and complex shapes, usually. They're the complex ones, though. The way we make them, is you've got basically a solid, long block of steel, and you heat it up to red hot. Not melted, but remember I said steel is very susceptible to heat. We know its yield stress decreases rapidly as you heat it up. So instead of it being able to be to yield at 350 MPa, when you heat it up red hot, it yields at a lower stress. So while it's red hot, we roll it back and forth. If you want to think about it as candy, it's very, very, very hard. If you heat it up, it gets malleable. So we roll it through these rollers and basically press it into the shape we want it to be in. And then once it's in the shape we want it to be in, we cool it off, and then we have the structural profile we need. As it cools off, it goes back to its normal yield stress, with one small caveat. We have some locked in stresses because of some of the weird kind of rounding bits and the way it's cooled off. So for hot rolled sections, we actually use a yield stress of 345 MPa. And we're going to see that again in a minute. I'm even going to add it here right into this slide. That's something I've never thought to do before. But slide 3, FY, and FY. It's not a bad idea to add it as many places as possible in my mind. So you can usually tell them they have tight, sharp corners at exterior bits, but there's fillets or rounded corners on all the interior sections. So what does that look like? Let me get a piece of this steel, this paper for a second. So I'm going to draw what I mean there. And if any of you have worked with steel or looked at steel or gone up and kind of really been paying attention as we've gone through this, you'll see what I mean. So really what they do is they take a blob of steel that looks like this and they put it through a hot roller, all right? And it squishes into shape. And ends up looking like this, okay? So see how that's a sharp corner and that's a sharp corner? But these ones are rounded because those are the ones where they're going through the hot roller. And so those are filleted corners. Hot rolling results in a black surface with areas of mill slag and is generally not suitable for exposed applications without some treatment. We'll often call it black steel because it looks very black and it'll rust on site very easily. But it's usually just the slag on the surface that's rusting. Cold rolled or cold formed shapes are manufactured from a piece of plate and they just get pressed into shape without heating them up. The plate is cut and then bent or rolled into shape and then welded if required. Cold formed steel is bright silver to the finish. HSSs are cold rolled sections. So what we do let me just draw this here. So for cold rolled sections, we would take this plate steel and roll it into this round HSS. And do you see right there? That's the seam where it would come together and get welded into place. Hot cold rolled sections have an FY of 350 MPa. All right, so here is what a hot roller looks like. You can see how it's been heated up red hot and it goes back and forth as these get into their final shape. Do you guys remember last year in the steel properties, I said that there was like groups of steel members, like the W310s. And it didn't mean they were exactly 310 millimeters in depth, but pretty darn close. Well, that group of 310s all started with the same kind of mill block and went through this machine and got moved into what it needs. I guess they were slightly different sizes because they end up at different weights, but they go through kind of the same block. Like they can only adjust those so much. So, these chunks of members are going to go through this roller here. Cold formed steel is literally just pressed into shape, just like that. All right, so we've talked about this before, but I'm going to say it again. The naming convention for W sections. Okay, so wide flange sections or I-beams. You'll often hear them called I-beams because they look like an I. D is depth, so that's the depth. B is the width. T is the flange thickness and W is the web thickness. The naming convention, for example, a W150 by 30, means it's around 150 millimeters deep. It is not exactly 150 millimeters deep. If you look in those steel section properties, that depth varies. It's pretty darn close, and they're all given the designation W150. The important thing is usually the second number, which is how much it weighs. And that's telling us how many kilograms per meter this section weighs. And the reason that's important is, remember, everything we're trying to do is build the cheapest building we can within our constraints. For steel and most materials, you can judge which one's more expensive by being the heavier one. So the lighter it is, the less it weighs. The heavier it is, the more it weighs. There is cost and complication and piece count, but normally it comes down to weight. So putting weight as the second part of the naming convention means it becomes very easy at a glance to tell which thing is more expensive. And so we want to go with the cheapest, which means we want to go with the lightest, which means we're going to go with the ones that have the smallest second number in W sections. It gets a little bit different when we're talking about certain other sections. But if we want to know the exact depth, we have to go look it up in the tables. All right, channels follow a similar naming convention. So a C200 by 21 is around 200 millimeters deep, but weighs 21 kilograms per meter. It tells us the approximate depth, but the actual weight, which we can use to compare cost, but no real dimensions. We have to look up the actual depth, the actual width, the flange thickness, and the web thickness. Angles. Angles are still a hot rolled section. You can see by that filleted corner here and here. So these would use a W, or they would use an FY of 345. I'm going to add that to all of these slides. And I think that's probably not a bad thing for you guys to see. But here the naming convention changes because we are putting exact dimensions in the name. So an angle, which we represent with an L, it tells us exact dimensions. So 102 by 76, and then this is the thickness of 9.5. So it tells us the real dimensions, but not weight. But look, if I had a W102 by 76 by 9.5, and I was comparing it by a 102 by 102 by 9.5, which one's going to weigh more? The one that's bigger. All of a sudden, these ones become a little bit easier to visualize which one's going to weigh more. So it's not embedded in the name, but we could usually tell which member is going to be heavier. Hollow sections. So these ones are cold rolled sections. So these ones would use an FY of 350 MPa. And we have round, square, and rectangular. So remember, these started as a flat plate and get bent into shape and then would be welded up on a seam. Now, elliptical exists. That's something that I have every 4 years, say, somebody shows up in town representing a company that makes elliptical HSS shapes. They give a presentation. The next project, architects always want elliptical HSSs. So the next architect that says they want it, I'll spec it on the project. And sometime in there, that particular company either goes bankrupt or we find out there's like a 10-month lead time to get them because they're only made in Europe. And essentially, I've never actually gotten them put on a project. What I have seen happen is this. So structural round HSS, and then plate steel welded onto it. The seams ground smooth, caulked, and then it all be painted. So it looks like an elliptical HSS, but the structural part is actually just the round bit there. I will say that there are some architects that are highly offended by this process because it's not representing the true structural form. So that is something I would leave to you to it's not gonna let me, oops. Sometimes just a quick button lets me get rid of that. Why won't it let me? Sometimes I just have to press a button and it leaves the drawing feature. Doesn't, damn it. Sorry guys. That is laser pointer highlighter eraser. All right, I'm just gonna do it that way. Okay, so in the naming convention for an HSS, the depth is D, B is the width, and the wall thickness is T. And you can see that right here in the name. A round HSS wouldn't have this second dimension here. So it would be HSS 152 by 6.4. You can tell it's round because it's only got the one dimension. So there are some other uncommon shapes that we're not going to use as much. HP shapes are often used. Actually, I don't use them that much. Sometimes you'll use them for piles because they're quite stocky. M shapes are very light, super light beams. WTs are structural Ts where they're really just a piece of I section cut in half. Cold form sections. WWFs are interesting. So when you get to steel sections that you've maxed them out, they don't work, you do have one other option, and that is to create your own. It's very expensive, like really very, very, very expensive. The desire has to be real. We're a client that understands the costs in this. But you can make your own W sections. You can take 3 pieces of plate and weld them up. So that's 4 welds for a huge portion of its length. Now it doesn't have to be full length unless it's outside. You're going to need that to be a full length weld. So the amount of time that goes into creating those is a lot. They're very expensive sections. All right, here's a reminder, our full stress strain curve. Yield stress is 355 MPa unless we've hot rolled the section, and then it's 345. But remember, that's the stress we care about. Except for every now and then, for a few discrete calculations, we'll use the ultimate stress of 450 MPa. But most of the time, 350 MPa is, or 345 if it's hot rolled, is the value we care about. Because what we want to do is we just want to know when it gets into full plastic deformation. So sometimes we'll say just when the extreme fibers start to yield, and then some members will allow it to yield all the way down to the neutral axis. But we don't want to go past that, because if we go past that, we're into very large deformations. We don't want to see very large deformations. If we see very large deformations in steel, which is different than exceeding our deflection limits, if we see very large scale deformations, it's because we've exceeded our strength criteria, which I know can be confusing, that if you've got a steel member that's bent all the way in half, that we might call that not a deflection problem, but a strength problem. Well, that's because we've exceeded the strength yielding limit here that we've defined as our life safety criteria. Damages to finishes on a beam that's deflected too much is something different. It's still safe for life support, so you could stand on it, you've just destroyed your drywall. But if you've got that really harsh, extreme bending on a steel member, it's because it's yielded. Okay, so typical steel properties. Fy is 350 MPa for HSS sections or cold formed. Fy is 345 MPa for our W sections, our channels, and our angles because they're hot rolled. Fu, or our ultimate, is 450 MPa. E is 200,000 MPa. And G, if you remember I said was a property we don't have to calculate, but it's related to E through the Poisson's ratio, which is really how much it bulges when it's squashed, is 77,000 MPa. We didn't really talk about where it came from, but I'm giving you the value. All right, steel reduction factors. Some of you have probably figured out what the main steel reduction factor is because you've seen it pop up in some equations, because I wanted to be giving you equations that made sense later if you went back and looked at them, but we haven't learned all the information yet. So steel reduction factor is 0.9. So we take this 350 or this 345 and we reduce it by 0.9. So we only take 90% of its capacity. So we say, here's the capacity. After this, the steel doesn't work, but we're going to drop that value just a little bit as well. Okay, we're going to break our design up into two components, tension resistance and compression resistance. So we're going to have a tension capacity equation and a compression capacity equation. Compression is going to get a little more complicated. Tension's easy. Look at this. I'm pulling on this. But with much less force, I'm squashing this. And something funny starts to happen. We're going to have to think about buckling now. So it's not going to be just about strength. There's something else happening embedded within our strength equation. So tension resistance is easy. It's all about strength. So the tension resistance is the least of TR equals stress times AG times Fy. Well, what's AG? We're really talking about area. The reason that little g is there is because we're talking about the gross area. Not like, that's disgusting, but the whole cross-sectional area of our steel member. So do you remember we had our equation here of stress equals force over area? Look, this is just rearranged. TR is, we've just said, we're talking about a force that is T. We get to use the subscript R because we are talking about this having a reduction factor on it. So remember, when we talk about a reduction factor being applied, we get to start using the subscript R. At stress, we know we're a little bit lazy writing Greek symbols, so when we're talking about our yield stress or our upper bound, we'll use the term Fy. So this equation here is really just a fancier way of writing stress equals force divided by area. Our force is a tension force, because we're talking about tension. Our stress is our maximum stress we want to see on this. We apply our reduction factor to it, so we just add a little reduction factor here applied to Fy, and as soon as we do that, that tension, we get to put the little subscript R. So this is just a fancy way of writing this equation. Here's where we're going to add a little bit to this one. For tension equations, we say this is all well and good, and you can even put bolt holes through this, or maybe a pipe hole through it. But we do need to do a second check just in case. We will say most of the time, if we have a hole in something, sorry, that's not really there. That's being very annoying. Will it? Oh, that's a pain in the butt. Okay, so if that's a hole in our piece of steel, What we tend to say is that if this is an applied load here, kind of the internal stresses come down, and they, if we have like even lines of, imagine just stress flowing through this, or a force, these will bulge around this opening. If the opening is significantly small enough, we can distribute that force around the opening, unless the opening gets too big, and then we're going to be governed by where the opening is. Because you can imagine if this equation is about the force being applied and the resistance of the steel and the cross-sectional area of the element, well, right here we've got less area. But because of this ability for the stress to kind of flow around an opening, we use Fu instead of Fy. This is really annoying because we don't use Fu very often. We really don't. It's almost always Fy. And then the very first real equation I give you has Fy in one of the versions of it. That isn't the normal thing. This is very explicitly when we're going around an opening. So, how did I do this? Right, okay. So, reduction factor for material steel is 0.9. Ag is the gross cross-sectional area, or just area. ANE is the net cross-sectional area reduced for bolt holes or whatever opening we've got. So this is where we've taken material out of the cross-section. Fy is the yield strength of the steel, which the majority of the time is the thing we're talking about. And Fu is the ultimate strength of the steel. So remember, if we go back to this, that's this strength here. We don't often use that strength in our calculations, but we do sometimes, and this is one of them. Pin connections, we're not going to design, but here's a nice little equation for pin connections. Don't worry about that. We're not getting into that. So let's do an example in our steel tension element here. So we've got a brace in a building that has a cross-sectional area of, or it's got dimensions of 100 millimeters by 200 millimeters deep. So 100 millimeters wide by 200 millimeters deep, but it has a 60 millimeter diameter pipe opening through it. What tensile, which means TR, because T is tension, capacity does it have if it's using 300 MPa steel? Now, this is a pain in the butt. I shouldn't have done 300 MPa steel because that's pretty much a done thing now. In fact, I don't even think I'm going to cross this out. We're not going to do 300. We're going to do 345. Or 350, sorry. Because this is not a hot rolled section. It's just a chunk of steel. So forget that the question has 300. I'll update this in the slideshow, so you won't see it that way, and I'll update the calculations I do here. So we've got 100 by 200 with an opening in it, and we've got 350 MPa steel. So we want to know what tensile capacity does it have, or what tensile resistance do we have. So let's go through this calculation here. Okay. So what we've essentially got, they've said that this is a brace. So this is our, it's better here. Oh, that's horrible, isn't it? Okay. So this is our tension example. What we've got in a building is we've got a frame of some sort. We don't know what it looks like. And we've got a brace element in it. Okay, this has a cross-sectional area, and somewhere here, there's a pipe going through it. So we know that normally its cross-sectional area would look like something that right there, and at the opening, there would be a cross-sectional area like that. So was it cross-sectional area, or was it a brace? Yeah, it was a brace. Okay, so normally, so just to give you kind of an idea of what we're drawing here, if this is kind of what we're talking about, we've got this opening in this member here, right? So if this is 200, and so it's 200 by 100, we know what the normal cross-sectional area is, and then we also want to check what its capacity is where we go through the bolt hole. So we'll get to that in a second. So let's write out what we know. So what we know our steel Fy equals 350 MPa. We know our steel Fu equals 450 MPa. We know our E equals 200,000 MPa. We know that our reduction factor is 0.9. We know that we had a depth of 200 millimeters and we have a width of 100 millimeters, and we have a hole with a 60 millimeter diameter, which I know that diameter is often written like that. What a total pain in the butt, because it's also the same symbol we use for reduction factor. Let's say diameter, just so we're not too confusing here. And so that means that dimension right there is 60 millimeters, okay? So we want TR, and there was 2 different calculations for TR. Now, remember, that is the capacity of the element. We want to make sure we don't go over that value. We're about to calculate 2 different equations. If we don't want to go over either of them, we're going to have to pay attention about what the ultimate capacity is. So the first equation that we had was TR equals reduction factor times Fy times Ag. And Ag was just the gross area. Well, we know our reduction factor. We know our Fy. And Ag we don't know, but we know we can calculate area because it's D times B. So it looks like we can calculate TR. 0.9 times 350 times 200 times 100. So it looks like we can actually calculate this here. All right, we've got 0.9 times 350 times 200 times 100. So it looks like we get 6,300,000 newtons. So this is important that this answer is in newtons. We have to remember that we often write forces in kilonewtons. So this would be, we would often see this written as 6,300 kilonewtons. Now we also had to check its capacity through that bolt hole. Now, we could check it right here where the hole starts to appear. We have to check it everywhere across that cross-section of that member. So if this is our normal cross-sectional area of this, where this is 100 and this is 200, at first the hole opening just starts to appear, and then we get bigger and we get bigger and we get bigger, and then it starts to get smaller again as we kind of like shift our cross section down the length of this. Well, we want to know where it's the worst. Where it's the worst would be cutting this right through the maximum of that. So right where our opening is 60 millimeters across. So what we really want to know is what's this area right here, okay? So our other equation that we had was TR equals 0.85 times our reduction factor times our net area at the hole times FU. Now, we don't often use FU. It's in very specific equations, usually where we have the ability to kind of distribute force around an opening. It's not the thing we use the majority of the time. So we have 0.85 times 0.9. ANE, our net area, is going to be our 200 times 100 minus 60 times 100. Or sorry, minus 60 by 100. Or we could say what we're left with right here is 200 minus 60. So 200 minus 60 times 100, and then times our FU, which is 450. So this is just that net area, which is just these little bits here left on the side. So we can plug that into the calculator. It's 0.85 times 0.9 times 200 minus 60 times 100 times 450 equals 819,500 newtons. We like to divide that by 1,000 to talk in kilonewtons. So 4,819, you might say 20. I'm just going to put the 0.5 for now. Kilonewtons. So what is our resistance capacity? What is the maximum load we'd want to put on, or what's the maximum factored load we'd want to put on this element? All right, so if we put a load of 4,000 kilonewtons on this, would it work? Yeah, because it's less than both of these. If we put a load of 5,000 kilonewtons on this, would it work? Well, it works for the overall capacity, but at the hole, it doesn't work. That factored load would be greater than the capacity at the hole, so it doesn't work. That means for this member, in spite of having calculated both of these, we would say that the tensile resistance is this value. It would work everywhere except at the bolt hole, at the pipe opening or whatever opening it is we have. And if it doesn't work there, it doesn't matter that it works everywhere else because the member would fail. So we would say TR equals 4,819.5 kilonewtons. I often put a nice big box around this so somebody looking at my calculation sheet can find it right away. Now, you're saying, what the heck? Well, working in an engineering firm, especially on a large project, if a bunch of people are working together, you would do pages and pages of calculations, and somebody else needs to come along and see what's going on, or it's a year later and they're making a change. They need to see what the final answer was very quickly so that they can see if they're able to make certain changes. Now, we do most of the work in Excel. When I started, this is literally what we did. We would take a piece of paper and we had a project binder, and it would get filed in the project binder in a particular order. We had a title block and we'd label everything. It was a very precise procedure. Now, I do all of this stuff in Excel, and I would highlight that Excel cell red to make it clear that this was the answer. I would often even embed elements, because now what we would want to do is this less than some TF? That's the question we would ask. We don't know what the load on this was, so that wasn't a relevant question this time. But remember, we want to make sure TR is greater than TF. And so we would find some factored load on this, and then we would want to make sure the capacity is greater than the factored load. The reduced capacity is greater than the factored load. Okay. All right, let's make me smaller. Wow, you can tell it is very early in the morning. It's not fun when I put that on a very large version of myself. Okay. Also got weird shadows happening. There we go, that's a little better. Okay, so compression squashing. So I will fix this slide so that it is not the 300 MPa. I'll go through and change that. Okay. Compression squashing. That was our tension value. We know that it was our stress equals force divided by area equation. It's pretty simple. We know what our cross-sectional area is. We know what our maximum yield stress is, and we reduce it some. And we were talking about tension, and once we talk about tension, we're talking about a reduction factor, we can use TR. Squashing gets a little bit tricky. We've got, if this was short enough, like if I've just got a little short little block here and I squash it, you can see it squashes quite nicely. No problem. What happens as I get longer? It squashes, so you can see it visibly squashing, right? Make it a little bit longer, so I'm holding it here. Make it a little bit longer. It squashes some, and then look what happens. I'm not doing that. It's doing it on its own. So I make it a little bit longer. It squashes a little bit, and then it buckles right away. And then when it's really long, I barely get any squashing. You can see that I don't even really get the opportunity to squash it. It buckles. So it looks like when it's short, it squashes beautifully. When it's at the halfway height, it squashes some, and then it buckles. And then when it's really long, it doesn't squash at all. It just buckles. So the squashing part is about when it's really short. And that is simply our stress equals force divided by area, where Py is the load that it yields, Fy is the yield stress of the material, so the maximum stress we want to put on it before it yields, and area is the cross-sectional area of the member. That's easy. Remember, area is just a shape property. So it's all about strength. When it's slender, so that was when it was short. When it was short, we had a cross-sectional area and it tried to squash. When it was really tall, there's a load where it tries to buckle. So we have a critical buckling load. So the critical buckling load, and so even a squashed member or even a stocky member would buckle, but it's kind of irrelevant because it squashes first. So there is a value where our element would buckle. It's got a somewhat complicated equation here. I felt like just wanted to check something. Okay, no, it's fine. So PCR is the critical buckling load, or the buckling load. Pi is easy. E is the modulus of elasticity of the material. That's easy. I is the moment of inertia in the direction that the member is allowed to buckle. So remember when we were talking about things bending last week? And we were talking about Ix. It was bending about that axis. But I said that if we did something like that, that would be Iy. So we can bend it this way about its strong axis, or we can bend it this way about its weak axis. When I'm squashing this and it's buckling, what direction is it going? It's going in its weak axis. It's not trying to buckle in its strong axis. So that means it's failing in a weak axis direction. So it's buckling in its weak axis, which means it's buckling about the YY neutral axis. And that's important simply because all of those charts I gave you give you values for I and S in Y and X directions. And then there's this KL. Well, L is length, that's pretty easy. So PCR is what we're trying to calculate. Pi is a known value. E is all about the material. I is a shape property. Length, L, is the height of the member, and we know what that is because we're picking whatever this member is or how long it is. We're the ones designing the building. What's K? So K is the one thing we don't really know here. This is a weird equation. You don't know what the heck this equation is. I'm telling you, it is the critical buckling load, but that's really all you know. That's what value it'll buckle at. But the things within the equation are all things we know so far, except K. It is the effective length of the member. So it's easy to look at this member and say, okay, its effective length is its height. That's great. So it buckles like this. Now, normally I have a student come up and do something here for me, and this is really hard to do by myself without looking foolish. I've used Dave in the past, but he's downstairs on the treadmill. So when I try to buckle this, maybe I can do it like this. All right, if I put my finger right here and I try to buckle this, look at this. I'm pushing way harder than I had before. It's not buckling. It did not take much. So the amount of load that I feel going into this finger here, stopping it from buckling, is a fraction of what I'm pushing down on. I can tell you statistically it's about 2%, but that's beyond what we need to talk about here. So it doesn't take much to prevent something from buckling. There's also a second thing. So that would be its effective length. So normally its effective length is its height. If I put this here, its effective length is half its height. Now, in fact, it gets even slightly more complicated than that, but don't worry about it too much. There's also a different thing that happens. So normally we're talking about pinned elements. If this was moment connected and I tried to buckle it, so a moment connection means this stays at 90 degrees and this stays at 90 degrees. When I try to buckle it, look at that. It has a different shape, and I can tell you I'm pushing a lot harder here. So K is all about how we would treat the shape of it. This has nothing to do with strength. Fy or Fu is nowhere in this. It only depends on the weak axis stiffness of this element. So this is all about stiffness. The first part, or the thing we looked at here, was all about strength. So there seems to be two things. When it's short, it seems to be all about strength. And when it's tall, it's all about stiffness. Okay, so here's just a chart of effective lengths. Don't worry about it. We're going to use this right here. I'm only going to make you use a K of 1, which means it's a simply supported column, just doing all the normal stuff a column does. If we ever did anything different, I would give you that explicitly. But I just wanted to show you what's happening here. So this is what it looked like when I was holding it and keeping it at 90 degrees top and bottom because it was moment connected. All right, this is a beautiful equation and again makes a fantastic exam question. So if I have a particular cross-sectional area member, I don't know, a W310 by 39, whatever, I can check what's happening. I can calculate what the squashing resistance of that member is. Remember, that's just stress equals force divided by area. Our area doesn't change. So as my element gets taller and taller and taller and taller, the capacity of it doesn't change. So for squashing, it doesn't matter how tall my column gets, the capacity at which it would fail due to squashing, doesn't change. When this was really short, I couldn't even get it to buckle. So if I calculated the critical buckling length, and say in blue, when it was really, really short, this eventually approaches 0 here, as you get shorter and shorter and shorter, you can see the load goes up, and it goes up drastically, like it's off the chart here. As I got a little bit taller, got easier to buckle this at, until I got all the way to a really tall element. So at a really tall element, I could see that it buckles very easily. So this is based on height. This is what load it would buckle at based on height. This is what load it would squash at based on height. And it doesn't change because height is irrelevant in the strength component of it. So what we care about is, does it fail by squashing or does it fail by buckling? And we saw that somewhere in the middle, I could squash it some and then it would buckle. So there is some combination of squashing and buckling happening within there. So our final CR equation that you haven't seen yet is a component of squashing. And look, when it's really short, it's governed completely by squashing. And when it's really tall, it's completely governed by buckling. But look what we do here. At a certain height, we say we don't give a flying toot that it has some capacity. It is so likely to buckle that we just don't care. We give a hard, flat no. You cannot use this column for any load whatsoever. We give a hard stop here, that this is the maximum capacity, no matter what your height is, of this element. So if it's taller than this, no, you cannot use this element. You just can't use it at a height over this. So what the heck is the equation of this red line? This equation was easy. We knew it. We've talked about it for a few weeks now. This equation, you were like, getting a little bit panicky. Looks a little weird. How do we combine the equation of the purple and the blue? Now, this isn't something you have to derive. There's been people doing statistical analysis on this for years and years and years and years and years, but there's a published value for this CR, or the compressive resistance of a column. Here it is. CR equals the reduction factor times the area times Fy times, in brackets, 1 plus lambda 2n to the power of minus 1 divided by n. I'm sorry the equations get so ugly at this point, but they come from somewhere. What we're saying is essentially, if this is really short, all of this goes away and has nothing to do with what we're calculating. So if it's really short, this is our equation. As it gets really, 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 really tall, this starts to take over and reduces this so much that it's completely governed by buckling. Lambda is basically our buckling factor. That's what I usually tend to refer to it as, is our buckling factor. So look at this. Here's that equation we had looked at on the other page, slightly rearranged. It's really just about the yield capacity relative to a critical stress that it would buckle at. Don't worry about it too much. Here's the equation we're often going to use. There is an R in here. I've added another little element in here. Do you remember when I gave you all of those shape properties last week? And I said there was a few other things we would make use of. R is one of the shape properties. And so you will see in there an R shape property as well. But remember, we care about weak axis buckling. So this is just basically a rearrangement of that critical buckling equation. So we looked at it. We're not going to use the equation in that form. It's been rearranged and modified, but this is where it's coming from. R, instead of using IYY, which is the stiffness of it in the weak axis, we're going to use RYY. So anything that has to do with buckling is usually the weak axis value. Okay, so CR is what we're looking for. Reduction factor is the material factor, which we know is 0.9. A is the cross-sectional area. That's easy. We can either calculate it if it's like a rectangle, or we can look it up if it's something like a W section. We have tables. I gave you those tables. We can look up the cross-sectional area. Fy is the yield strength of steel, which we know is 345 for hot-rolled sections and 350 for cold-rolled sections. Lambda is something you don't know, but it's KL divided by R times the square root of Fy divided by pi squared E. Okay, well, let's look at that. K, I've told you, is usually going to be 1, unless I tell you otherwise. It'll be 1. L is the unbraced length. So if it's not braced, that's the full height. If there's something here stopping it, well, it's only going to be half the height. So we know what L is. R we know is a shape property we can look up, and it's going to be in the weak axis. So we're going to look in those shape properties for R, Y, Y. Times the square root of, well, Fy is our yield strength. Pi is a constant, and E is something we know for steel. It's 200,000 MPa. The last thing we don't know is N. Now, I don't want you to worry about N. From the equations we're going to do, N is a constant. Usually N is this constant. I do a lot of calculations where N is not that constant, but that is way beyond the scope of this course. So for you, N is a constant of 1.34. So that means we know, or we can look up all of these things. But look at this. There looks like there's a limit on this. CR is 0 if KL divided by R is greater than 200. Let's just go back to this. That's this limit here. So here's our CR equation. It comes along, but we don't care if its height, if its KL over R is greater than 200, CR is 0. So we put an upper bound on this. This is the maximum that we will possibly go. We won't let it go taller than this. All right, we're gonna have to do some calculations, I think. Here's the big statement. Do we have to calculate this every time? Yes. No, we don't have to calculate this every time. We have to calculate it a few times, and I give you an example in the assignment, I believe, about why it's still important to know how to do it. For an example, maybe an old building is being renovated and we're putting new things on the roof. Steel, that's 350 MPa, only became kind of ubiquitous in the industry a few years ago. When I started, plate and angle and channels were often only 300 MPa. That's why some of my examples still show 300 MPa. They finally just kind of got rid of all of that elements recently. So 350 MPa is now what we would spec on drawings. In the 70s, it was a different strength of steel. So we've gotten better at making our steel. E has stayed the same, but our yield strength has increased. All right, so if we don't want to calculate that every time, what can we do? Well, in this steel book, of course, there are column design tables, which means at those heights, they've created exactly this. They've gone through and picked points, and they've checked these values, and they've used that equation to create CR and plot this graph. And then they've just made a chart of it. So instead of for every element giving you this graph, they've given you a table with these red dot values. What do we do in between these red dot values? Well, in between them, we often draw a straight line. And it's the amalgamation of those straight lines that make it look like a curve. If we want something in between those two red dots, we interpolate. And remember, we can interpolate from a chart as well. So, an HSS 127 by 4.8, that's 3.975 meters tall, or 3,975 millimeters tall. All right, we've got a chart here that shows a round HSS that matches ours. Here are the HSS 127s, and there is one here that says 4.8. So it looks like we care about stuff in this line. I'm telling you that K is often going to be 1. This says effective length KL. All right, so we have a K of 1, and that's our L. So our KL is 3.975, or 3,975 millimeters. So we can look at this chart, which means we're somewhere in between 3,600 millimeters and 4,000 millimeters. So we know we can interpolate between these two values here. Now, what do you think it's going to be? Is it going to be closer to the 4,000 or is it going to be closer to the 3,600? Before we interpolate, this is always a gut check I like to do. If this is our height, is it closer to the 3,600 or is it closer to the 4,000? It's pretty darn close to the 4,000. So when we interpolate, just do a quick check and make sure that you're closer to this value than this value. So we know we've got our HSS, we've got these heights, and this is our chart. So we can see our possible values here. So we're somewhere in between here is our compressive resistance. Look at this. Here, as we get tall enough, there are no published values because that's where KL divided by R is greater than 200. So we have no compressive resistance here. Even though we could calculate and have some compressive resistance, we say there is no compressive resistance. Okay, so at 3,600, we've got a CR of 309 kilonewtons. And at 4 meters, we've got a CR of 272 kilonewtons. That makes sense. As it gets taller, it buckles easier, which means it can support less load. We want to know what it is at 3.975 meters, so we can interpolate between these two values. And it looks like we get a CR of 274.3 kilonewtons if L is 3.975 millimeters. Sometimes I'm lazy and I'll just take this upper value one, but they've asked us for the exact value here. So CR for a column that is 3.975 millimeters tall or meters tall has a compressive resistance of 274.3 kilonewtons. We did it. If you wanted, go use that compressive resistance calculation and see how it shakes out. It'll be really darn close to this. They didn't calculate it on this exactly. We interpolated between two values, so it'll be slightly different than this, but it'll be pretty darn close to this. All right, you're designing a steel canopy for an existing building in Brampton. The height of the canopy is to be 4 meters and matches the existing building. That tells us something about snow load there. The snow load for Brampton is SS equals 1.3 and SR equals 0.4. Assume the following assembly: 4-ply roofing with gravel, 38 millimeter deck, that's 0.91 millimeters thick, 12 millimeter gypsum wallboard soffit, allow 0.24 kPa weight allowance for structural steel. The architect wants to know if an HSS 64 by 64 by 3.2 using an FY of 350 MPa steel works. Try using the column selection tables and verify your sizing by calculation from basic principles. So use our big ugly equation. What about a W150? So they have two specific elements they're asking us to check. And remember that when it's a W150, FY is actually 345 MPa. So we have two columns we can calculate by hand here. I think one of the things I'm going to do and add into your slides, actually that might be fun to do. I might do another example for you if we have time here, because I don't think this is a very long lecture after we go through this. Okay, so let's take a look about some things on this example here. We know nothing, really. We have to figure out everything. This is exactly what would happen in a project. We have what the roof assembly is. We know where it is, so we can look up some climatic data. We know the layout of this, but it looks like we're going to have to figure out the worst case load on the roof. We're going to have to figure out the tributary area, which means then we can figure out what factored load is on this column. And then we can figure out what the reduced capacity of this column is. And then we can make sure that the reduced capacity is greater than the factored load. And if all of that happens, we have a column that works. So it looks like we've got 5 meters by 6 meters for our canopy. So that's some information that we have. So let's start going through this calculation. Okay. I am going to quickly just see what this told us if we did the sizing guidelines. So steel column example. If we use the sizing guidelines, it told us that this had a height of 4,000 millimeters. Our good old sizing guidelines that we talked, this is a bit funny, I'm gonna try this here, yeah. Our good old sizing guidelines that we used a lot last term and you're gonna need for your project was D equaled, or W equaled H divided by 20. So we have 4,000 divided by 20. If this was a preliminary set of drawings, 4,000 divided by 20 equals 200. I would probably, on a preliminary set of drawings, say an HSS 203 by 203 would be a really good column to put on a preliminary drawing set. But remember I said those weren't the answers? And what if that column was on the top story of a 50-story building versus if it was on the bottom story of a 50-story building? So these sizing guidelines are great, but they only look at a narrow snapshot and they have nothing to do with loading on it. So we now have the ability to find out what member might actually work. So we need CF to be less than CR. That means we have to calculate CF and we have to calculate CR. Let's take a look at the factored side first. So this is everything we did last term. So we want to find out the factored load. Okay, well let's start with the dead load. The dead load, they gave us a breakdown. There was 4 ply with gravel. There was 38 metal deck. They told us it was 0.91 mils thick. A 12 millimeter gypsum wallboard soffit. I'm going to say this is a canopy. It's outside. That's the dumbest choice ever. Don't worry about it. I just wanted something that we could pull some easy numbers off. And then steel, they gave us an allowance of 0.24 kPa to use for weight. The other things we have to go look up in our dead load chart. Let me pull those up for us. Hold on a sec here. Dead loads. Let me bring this over here. Oh shit, kid just woke up. Okay, I'll have to finish this in a bit. Okay, so we'll keep looking at these values. Let me make this smaller. My youngest did in fact wake up at 6:30 in the morning, and he's now working with me. We've got headphones on him. If you hear random yelling, because he's a small child, he doesn't understand that when he has headphones on, everyone can hear him just fine. So you might randomly hear him yell something out at a volume that blows up your speakers. So I apologize in advance for that. Okay, so what were the things that we needed to look up here? Well, the very first one was roofing. Let's come over to our roofing section. It was a 4-ply asphalt with gravel, which meant it was 0.32 kPa. So I'm not going to make the screen big, but I'm going to write it down right here. 0.32 kPa. The next one was metal deck. Now, there is over here a deck slab, which would be 38 deck with concrete. That's not what we have. We have just a regular old metal deck. So a steel deck, 38 millimeters deep, up to 0.91 millimeters thick. We carry an allowance of 0.1. So 0.10 kPa. The other one was 12 millimeters of gypsum wallboard. So gypsum wallboard shows up in a few places on this, but look right here, there's one in roofing where it says 0.08 millimeters per 10 millimeters.
What? Grapes?
Grapes, yeah. We have 12 millimeters of it. So I'm just gonna, 1.2 times 0.08 gives us 0.096 kPa. Okay, so we have, let's make this bigger. We have all of our values written in here. We can sum these up. 0.32 plus 0.1 plus 0.096 plus 0.24, we get 0.77 kPa. We have a dead load. Fantastic. If you guys remember, snow load. Is it an alien ship, Duncan? Okay. Snow load.
That one's on the ground.
Okay. That is a cool alien ship. Snow load, they gave us SS equals 1.3 kPa and SR equals 0.4 kPa. We could have looked that up out of the climatic data. They told us where this project was, so we know we could go to our climatic data and find SS and SR. SS is basically how much snow could fall, or the weight of the amount of snow that could fall. The snow load equation is IULS times SS times some factors of CB, CS, CW, CA plus times SR and bracket. So remember, SR gets added to the SS with its factors before applying the importance factor. We also have our serviceability case as well. So we need our I value. So we also do this for SLS. I equals, well, actually, let's write these out here. I equals 1 or 0.9, depending on if it's ULS or SLS. There was nothing in this equation that said that this was an important building in any way. So we are going to go under the assumption that it's a regular importance factor building. Unless I tell you otherwise, that's what I'd like you to assume. SS, we know. CB is the ground snow load factor, which I've told you we're going to use 0.8. Just don't worry about it. We're going to use 0.8. CS. Hold on a second, everyone. I feel like I just heard Malcolm scream now. He can come down and find us on his own too. Okay. CS, it's our slope factor. It very much seemed like this was a flat roof. There was nothing that gave us any indication otherwise. That is another child awake. Holy frack. Okay, so there's nothing that tells us that this roof is sloped, so its slope factor is going to be 1. CW is our wind exposure factor. I told you it is very hard for it to be anything but 1. We've got a factor of 1 there. That means the snow is not going to blow off the roof. You basically need a very open region for that to happen. And then CA is our accumulation factor. That would happen if our canopy was low and our existing building was high and snow blew off of it and piled up on the canopy. It said in the equation that the two roofs were at the same height, meaning that our CA would be 1. So now we can calculate our SL for ULS equals 1 times 1.3 times 0.8 times 1 times 1 times 1 plus our 0.4. And so we have 1 times 1.3 times 0.8 times 1 times 1 times 1 plus 0.4 end bracket, and we get 1.44 kPa. Okay, that's our load that we will use for strength calculations. And for serviceability calculations, we know we get to take 0.9 of that, essentially. So everything else stays the same. Which is 1.30 kPa. Okay, so we've got some snow loads now. So we have a dead load and we have a snow load. Seems like we could probably figure out the factored load on the canopy.
Hi, Mom.
Hi, baby boy. Okay, factored load. All right, the factored load, we have to look at a few different load combinations. Dead by itself could govern it. We know we could have dead with snow and live, but they didn't tell us there was any live on the roof. So it seems like dead and snow together are the one that could govern this. So for dead by itself, it's 1.4 times our dead load, which is 0.77. And for dead and snow together, it's 1.25 times 0.77 plus 1.5 times our 1.44. Let's take a look. 1.4 times 0.77. Now I told you guys last term, and we did an example, the dead load has to be really high to ever govern this, but it's worth checking every single time. 1.25 times 0.77 plus 1.5 times 1.44, and we get 3.12. Interesting. My example, I use... Let me just check something here. All right, up here when I added up my dead load, I'm used to that being 0.25. It looks like I did 0.76. Sorry, 0.76 kPa. Nominal difference here, just I want these answers to match what I did in the worked out example that is in the slides. So that's just 1.4 times 0.76, which would be 1.06. These are like such small changes, but I just want you guys to be able to see the math work through all the way. So 1.25 times 0.76 plus 1.5 times 1.44 equals 3.11 kPa. Okay, we have a factored load. We aren't using it much in this week, but let's look at our serviceability loads as well. So serviceability dead in snow and serviceability snow. These might be handy for us later on. We know serviceability dead in snow is our 0.76 plus our 3.1 plus our 1.30 kPa because it's our serviceability snow, and serviceability snow by itself is our 1.30 kPa. So 1.3 plus 0.76 equals 2.06 kPa. So this is our serviceability dead and snow, and our serviceability snow was 1.3. So we have the loads on the roof for all the different kind of combinations of things we might be interested in looking at. What we haven't figured out is the total load on the column. If we go back and look at that example, we have our roof here. This is our column here. It looks like if it was a tabletop, you would imagine that it's taking a quarter of this canopy. And that canopy is 6 by 5 meters. So our tributary area is 6 divided by 2 plus 5 divided by 2. So 6 divided by 2, times 6 divided by 2 times 5 divided by 2 equals 7.5 meters squared. So that's the area that column is supporting, or a quarter of the area of the whole. So the whole would have been 6 times 5. If we divide it by 4, we have 7.5. So we're supporting 1/4 of that canopy on our column. So the factored load on our column, because these are factored loads, is 3.11 kPa times our 7.5 meters squared. 3.11 times 7.5 equals 23.3 kilonewtons. So we have our factored load on our column. Do you remember we spent so long figuring out how to do this last year, and now we can do it in just a few short minutes. Okay, so we have our factored load on our column. Now what we need to do is make sure that the compressive resistance of the examples they gave us, or the ones they asked us about specifically, are greater than this factored load. Okay, so let's take a look at the compressive resistance, CR, of our HSS 64 by 64 by 3.2. All right, we know that the equation for CR is the reduction factor times the area times Fy, and that would be just about strength, but we have to worry about buckling as well. So buckling is 1 plus lambda to the power of 2n, and then everything in that brackets is to the power of minus 1 divided by n. Okay, let's see everything we know. Let's write out what we know. So I often will break it out into what we know about steel. Well, for steel, we know the reduction factor is 0.9. Fy, we know for an HSS is 350 MPa. E, we know, is 200,000 MPa. What do we know about the member? Okay, well, we know that, well, for the member, let's look up a few things. Let's go look up our steel section properties. All right. Let's make me smaller here. We've got steel section properties right here. Let's find our HSS's, shall we? So that's somewhere further down the line. HSS's, okay. So an HSS 64 by 64 by 3.2. I passed the square ones here. So an HSS 64 by 64 by 3.2. Look, we've got all kinds of stuff. We've got a mass, we've got a dead load, we've got area, we've got I, we've got S, we've got R. They don't have it in IXX and IYY, SXXX, SYY, RXX and RYY. Why do you think that is? This one's symmetrical about both axes and they're the same. So all of these things about the y-axes are the same about the x-axes because it's a square. So that means that we can look up the area of our HSS 64 by 64 by 3.2 is 741 millimeters squared. 741 millimeters squared. And the other thing we know we need is our R, which is 24.4 millimeters. Okay, so that's a weird shape property that we didn't talk much about, but we know that it's something that we can look up. We could have calculated it if we wanted, but we can look it up. Okay, so we've looked up our area is 741 millimeters squared. Our R is 24.4 millimeters. We need our I. Let's go back and look at our I as well. We didn't look that up. That was my bad. I. So I for our 64 by 64 by 3.2 is 0.441 times 10 to the 6 millimeters to the 4th. We know that this is something we can calculate, but we've looked it up, made our lives one step easier here. So we've looked up our I is 0.441 times 10 to the 6 millimeters to the 4th. The length or the height, the unbraced length or height of this member, they told us in the question is 4 meters. So 4 meters, which we know is the same as 4,000 millimeters in case we need it in millimeters. And K, I have told you, K is just going to be 1. We don't even need to worry about that. Other things, we know that pi equals 3.14. We know that n is going to be 1.34. And we know that lambda equals KL divided by R times the square root of Fy divided by pi squared times E. This came out of the critical buckling equation. We could have derived this from looking at the critical buckling equation, but that's a bit of a pain in the butt. I'm just giving it to you directly here. And then so within this, it looks like we have everything we need to calculate this CR. So let's take a look. CR equals our reduction factor we have as 0.9. A we have as 741. Fy is 350 MPa times let's make our brackets big here, times 1 plus lambda. So lambda, let's make brackets here. K is 1 times L, which is 4,000, divided by R, which is 24.4, times the square root of Fy is 350, divided by pi squared times E, which is 200,000. Thank you for the kiss, Duncan. All of this is to the power of 2 times 1.34, and then all of that bracket is to the minus 1 divided by 1.34. Yep, that's messy. That sucks. Hi, buddy. Okay, here's what I recommend. Calculate this in steps, or if you're feeling bold and brave, plug it all into your calculator. I'm gonna go ahead and plug this all directly into my calculator. I'm gonna take a risk. I'm gonna be bold. I'm gonna push the boundaries here. Maybe I won't. Maybe I'll do it in steps. What do you think? Yeah, let's do it in steps. Okay. All right. Maybe not. I'm gonna try it. Let's see how it goes. If I screw this up, I'll go back and do it in steps. Okay. 0.9 times 741 times 350 times bracket 1 plus bracket 1 times 4,000 divided by 24.4 times square root bracket 350 divided by pi squared divided by 200,000, and that bracket to the power of 2 times 1.34 end bracket to the power of bracket negative 1 divided by 1.34 end bracket. Let's see how I did. I did it in one fell swoop. Believe it or not, plugging all that into your calculator is a bit of a skill. You guys can break it up into steps, so don't worry about it. Calculate these bits up. Remember to keep your brackets in line and come down in stages calculating this out. You're going to find it very, very, very helpful. But when you go through and do that, you are going to calculate this out to be that it is, we've got it here as 44,000.
Mommy, can I have this?
909 newtons, which we know we like to switch to kilonewtons, is going to be,
Mommy.
hold on a second, 44.9 kilonewtons. No, you can't have that. That's a subscription. We're not going to do that, buddy. I'm sorry, buddy. Okay, so we've all right, we're going to stop now. Okay, so we've calculated the compressive resistance of the column. Now here's what it all comes down to. CF equaled 23.3 kilonewtons, and that is less than CR, which equaled 44.9 kilonewtons. It works, and so HSS 64 by 64 by 3.2 works. We have an answer. We have something that works for something in real life. So we have actually gotten somewhere very far today. We were able to calculate from beginning to end the full process that a structural engineer does in a process. Now, the first page we would have to do no matter what, but this second page we could look up in a table. But as you see, as much as it was a very intimidating equation, it actually wasn't a very hard calculation in the end. let's check and see how it compares with the tables that we would have looked it up in. Let me just open up our steel column tables and we can take a look at that. I'll make my screen smaller here. So let's come over to the steel column tables. So we have an HSS 64 by 64 by 3.2. Look at this. Here's our chart of things here. We had a KL of 4 meters, 45. We had kept an extra significant figure. They kept it at 2 significant figures, so we could round up and we would exactly have 45 as well. So it looks like what we did is exactly what they would have done to calculate all these values. Okay, there was a second part to the equation that they asked us to do. I would like to point out that our sizing guideline guessed that we only needed a 203 by 203. In the final design, we have something much smaller that works. That was a very lightly loaded canopy supporting a very small tributary area. The sizing guideline doesn't look at that. It doesn't look at tributary area and it doesn't look at the load. It just looks at the height. So you can see that those sizing guidelines aren't that effective, except that they can be very, very helpful. What they didn't do is tell us that we could use a much smaller column. So that's a very helpful thing. Preliminary sizing set, you might have drawn a 203 by 203, gone and met with your engineer, and then found out you could use something smaller. And that's just a pretty good solid win. Okay, the other question they gave us was calculating the CR So we have now CR of a W150 by 30. All right, let's take a look at what we know about the steel. So a lot of this is exactly the same as what we wrote out the last time. So our reduction factor hasn't changed. Fy has changed. It is 345 MPa because it's hot rolled. So that's the only reason this is different. It started out as 350 MPa steel. It was the same steel, but when it went through that hot roller to make it the shape of a W section, it has some locked in residual stresses that kind of lower its yield stress just a little tiny bit. Okay, E hasn't changed. E is still 200,000 MPa. The member. What can we calculate about the member? We know that we need A and R and I, YY, and R, YY. So these are things that we're going to need to look up. Let's go to our steel sections. We could calculate these, but we're going to look them up. We're feeling a little bit lazy. Like trying to take a guess here. Did I guess right? Quite close. All right, W150, W130, or W150 by 30. Here we are. Here's the member we want to look at. W150 by 30. 150 by 30, we need area. So our area is 3,810. And then we are worried about buckling in the weak axis. Remember, it's trying to buckle in the weak axis, not the strong axis. So we need IY, which is 7.07 times 10 to the 6 millimeters to the 4th, and RY, which is 38.6 millimeters. So let's come back and write those values into our charts here. So our area is 3,810 millimeters squared. Our RYY is 38.2 millimeters. And IYY, is that the value we looked up? Yeah, it was 5 point, I was looking at the wrong one there. When we were talking about it, I started looking at a 150 by 37, but the 150 by 30 is 5.56 times 10 to the 6 millimeters to the fourth. So 5.56 times 10 to the 6 millimeters to the fourth. Okay. We know that our length, which is our height, hasn't changed, is 4,000 millimeters. Sorry, everyone. And K, I've told you, is 1. We're just going to use 1. We don't even need to worry about anything else. Other, we know that lambda is KL divided by R times the square root of Fy divided by pi squared E. We know that the full compressive resistance will need N, which is 1.34, and we know that pi equals, well, if you want to say it, pi. So we've got all of the things here that we need to be able to calculate our compressive resistance. We know that CR equals our reduction factor times our area times Fy times 1 plus lambda to 2n to the power of minus 1 divided by n. Okay, we have everything we need to calculate this. Let's plug it in.
Meatballs everywhere.
I see. Did Cyborg cover everyone in meatballs? He's watching Teen Titans Go.
Yeah.
All right. We've got a reduction factor of 0.9. We've got an area of 3,810. We've got an Fy of 345. Let's get our big brackets going here. We've got 1 plus lambda. Lambda is KL divided by R times the square root of Fy divided by pi squared E. Okay, so K is 1 times our length is 4,000 divided by R, Duncan, is RYY, which is 38.2 times
Mommy.
Duncan, times the square root of Fy, which is our 345, divided by our pi squared times 200,000. Let's do that bracket, because then that is to 2 times 1.34, and then all of that is to the minus 1 divided by 1.34. Okay, we've got that all in there now. I wonder if I can press my luck and do it all in one go here again. So let's try to plug this all into the equation here. Whew. All right. Remember, you can break it into steps. There is no problem with that. In fact, you will see in the worked out example that I did exactly that, the one that's in the slideshow. All right, 0.9 times 3,810 times 345 times bracket 1 plus bracket 4,000 divided by 38.2 times square root bracket 345 divided by pi squared divided by 200,000 bracket to the power of 2 times 1.34 end bracket to the power of bracket minus 1 divided by 1.34. Let's see, how did I do? Woohoo! I did it again, 2 for 2. We got that all plugged into the calculator in one go. So we get 475,606 newtons. No, don't get it. Okay. We'll often change this into kilonewtons now, which would be 475.6 kilonewtons. Or we could just say 476 would be a pretty good answer to go with there.
Mommy.
Oh, hi, buddy. Okay. All right, so 476. Duncan, you're gonna knock everything off. Okay, 476 kilonewtons. But let's take a look at is CF equals 23.3 kilonewtons less than CR.
It's from the one that you did a long time ago.
Thank you, buddy. CR equals 476 kilonewtons. Yeah, it is. In fact, it is crazy much less than it. Looks like maybe it wasn't the greatest choice that we used. So that was probably over-designed. Let's just double check ourselves against the published values for this. Let me just make me smaller here. Let's go to the steel column tables. Let's find our W sections. All right, W150 by 30, 4 meters. Look at this, 476, exactly what we calculated. So that bodes well for our ability to calculate these things. Let's come back to our slides here. Okay, so it looks like we've calculated all the things they've asked us to. I've got those all worked out there. So we've done 2 examples here. We now know how to calculate the compressive resistance of a steel column. If we know kind of what the layout is, which is what you're making as the architect, we can see if that compressive resistance works for the factored load on our element. So here are the things to remember. Buckling and slenderness are related. So take the same member and make it short, it's going to be governed by strength. Make it tall or slender, it's going to be governed by buckling. This is one of those things you intuitively know in your gut. When you see a really small column, you know that it doesn't matter what the load is. You know if it's tall, it can carry less load. You get that intuitively. Stocky columns are more likely governed by strength. Slender columns are more likely governed by buckling or stiffness. And for something in between, it's a little bit of both. Okay, you should know the reduction factor, E, G, Fy, and Fu for steel. I will almost always give you all of these, and G I told you I will always give you, so don't stress about that too much. You should know how to calculate TR. You should know the interaction diagram of squashing and buckling for columns. Remember I said that makes a good exam question. Okay, you should know how to calculate the critical buckling load. You should know how to calculate CR for columns, which uses the critical buckling load embedded in it. And you should know how to look up CR for available columns. I'm wondering now, I think we have a little bit of extra time. I'm gonna go back to this column here and wing it off the cuff and see if we can calculate this CR value. It'll be pretty close to this, but we linearly interpolated between these two things. So let's see what we get possibly if we calculate it out by hand. So I haven't done this. We're gonna do it kind of off the cuff. There's nothing worse than trying to do math in front of people. It's super embarrassing when you're standing up in front of 100 people too. If I screw up here, I'll just stop it and then fix it and then turn the camera back on. Okay, in fact, I'm going to stop it for just a second. Okay, let's take a look at this column. We're going to check CR for an HSS 127 by 4.8. Where are you going, Duncan? An HSS 127 by 4.8 that has an H of 3.975 meters.
Mommy, can you pull this down?
I can pull that down for you, buddy. There you go. Okay, so this is a bonus example problem, all right, that I am winging it for. All right, what do we know about our steel? This is a good process to go through. Well, our reduction factor is 0.9. Fy, this is an HSS, so it's a cold rolled section, which means Fy is going to be 350 MPa. E is 200,000 MPa. For our member, for our member, we want to know our area, and you saw that we're not actually using I because there was two different ways to write out the critical buckling component. So we're going to look up A, our RYY, which we know this is just a round section, right? So it's going to be the same in both axes. L, we know, is 3,975, and K equals 1. So let's look up our A and our RYY for this member. So steel sections, let me pull down the screen here. So we want to get back to those round sections. All right. Oh, look at that. That was amazing. I just guessed at what page out of 62 this was on. So HSS 127 by 4.8. So it's the second bottom row in this category. We've got an area of 1,840 millimeters squared, and our RY is 43.2. So 43.2 millimeters. So it looks like those were the only things we needed from this. Okay, let's make the screen big again here. We know that lambda equals KL divided by R, but we have all of those bits of information, times the square root of Fy divided by pi squared E. And we know in our big CR equation that N equals 1.34. So we have pretty much everything that we need here. All right, let's try plugging this in. So CR is our reduction factor times our area times Fy times, in brackets, 1 plus lambda to the power of 2n, and those brackets are to the power of minus 1 divided by n. So let's write out our full equation here. We've got 0.9. This pen is starting to die on me a little bit. So 0.9 What are you doing, Duncan? No. Oh, you're pausing it.
I keep doing that.
Just for a few more minutes, okay, buddy? So 0.9 times our area of 1,840 times our Fy of 350 times bracket 1 plus lambda, which is K of 1 times L, which is 3,975, divided by R, and R is 43.2, times the square root of Fy, which is 350, divided by pi squared times 200,000 MPa, and so this is to the power of 2 times 1.34, and then this is all to the power of minus 1 divided by 1.34. Okay, it's a little bit hard to see there, but you get the idea. Let's see if I can plug this into the calculator. We know we need an answer that's somewhere around 274 kilonewtons, somewhere close to 272, just a little bit bigger than 272. All right, let's plug this in. We've got 0.9 times 1,840 times 350 times bracket 1 plus, Duncan, stop, times bracket, Duncan, no, buddy, you can't do that. No, stop, Duncan. Duncan, I need like 2 minutes, buddy, 2 minutes, okay? No. Times 3,975 divided by 43.2 times the square root of bracket 350 divided by pi squared divided by 200,000 end bracket.
I not here?
I don't know, Duncan. Did you turn the volume down, buddy? I'm just.
Well,
Oh, what was that? Okay.
maybe my headphones died.
You turned them off, possibly? I don't know what you did, Duncan.
I didn't.
Okay, you have to wait just like 2 minutes. I'm almost done what I'm doing, buddy.
My headphones are dead.
You have to wait. No, they're not. Duncan, stop. Effer. Okay, where am I? And that bracket. To the power of 2 times 1.34 bracket, and that bracket to the power of minus 1 divided by 1.34 end bracket. Well, looky, even with all of those distractions. Okay, so this is why we can straight line interpolate between some pretty good values. We calculated 274.4. So if you remember that interaction
Can I have mandibles for Christmas?
that interaction diagram looked something like this. Okay, and if we I need you just a second, Duncan, okay? And so we looked on a chart and found a value here and a value here, and we straight line interpolated from there because we had something right here. Well, we just actually calculated it and got a value pretty close the same. Here, when the height was 3.6 meters, CR was calculated to be 309. Here, when the height was 4 meters, CR was calculated to be 272 kilonewtons. We here, for an H of 3.975 meters, linearly interpolated it to be 274.3, and we calculated it to be 274.4, which in the chart, if they actually plotted it, they would say 274. So there's another bonus example that's not in the slides, but you see the linear interpolation version, and so this was just an extra worked out example if you wanted an extra one. Okay, next week we're going to jump on to steel beams. Duncan, say bye to everyone. Duncan, say bye to all the students.
Bye.